So what I want to do over the next, it will be almost 30 minutes if you give me that time, is to give you an update on the latest science, which is summary, is shown here on the screen, which is, as you know, the Christmas Day Apollo 8 image of Earthrise. Is a very special version of it because you see the moon is on this very, very steep slope, which is one of the take-home messages that we are now at a point where we as humanity, as the modern industrialized metabolism, is posing so big pressures on the planet that we're hitting hardwired biophysical processes that regulates the very stability, the resilience, and the life support capacity of the Earth system, which means that the window for us to have a prosperous, equitable future is no longer anything close to linear change. It is about exponentials. It's about transforming ourselves back within a safe operating space of a healthy, stable planet. That's the point we've reached. And I won't be taking you into the lab of the deepest concerns we have today in terms of just the fact that over the last decade we see accelerated rates of warming, which we don't fully understand. We're seeing more and more signs of cracks in the buffering capacity of the Earth system. There's so many reasons for concern. What I will share with you is rather just where are we in a relatively strong consensus in science, and then zoom into what is required for us to unlock transformations, and is there still a window open for us to have a manageable, thriving, equitable future for humanity on planet Earth. So off we go. Well, to begin with, I'd like to go through the scientific evidence why we now need to have a world, our world, us as a global community, evolving, developing, moving within a safe operating space of a stable Earth system. And that we today have to scientifically define this based on three areas of scientific evidence: the Holocene, tipping points, and the Anthropocene. And I'll go through all three of those and just tick them off so that you're absolutely up to speed with why we are at this juncture where we now have to be stewards of the entire planet, and that we are focusing in on resilience, namely the ability of the Earth system to buffer and dampen stress, but also on the fundamental life support and the stability of the Earth system, because we are now, unfortunately, forced to ask the question, are we at risk of pushing away the planet to a journey that could self-reinforce itself, moving towards what we define as a hothouse Earth, which would be way away from the Holocene state which we've been in for the past 10,000 years. The first insight, then, is the overwhelming scientific evidence that we're now in the Anthropocene. Greek, anthros, humans, we are now in the driving seat. We are in an epoch where we are the dominant force of change. We're in the driving seat, running the change. The scale, the speed of impacts are unprecedented. This is, as you know, very well established, not from models, not from theory, but from observations. What you see here is the pressure points from the start of the Industrial Revolution until today. The red curves here are the hockey sticks of economic growth, population growth, resource use, everything that basically are manifestations of the globalized world economy that we live in. And here you have the impacts on the planet. And I won't go through all these slides. You know, on the upper left-hand corner, you have the only hockey stick we tend to focus on, namely on carbon dioxide. I can say you can pick essentially any parameter that matters for human well-being, that matters for the economy, that matters for social stability. They look the same. From 1750 up until the dashed line here, 1950, it's linear change. We have problems, but it's incremental. And then just 10 years after the Second World War, we're 3 billion people on planet Earth, and we put in the high gear of the exponential rise of pressures, and the planet is subject to this exponential rise of unsustainable pressures across basically everything that matters for life support on planet Earth. And now we are at the top of these curves with regards to biodiversity loss, with regards to greenhouse gases, with regards to ocean acidification, overfishing, deforestation. You pick what you want. There we are, the conclusion that we are now driving at a point where we are at risk of deviating away from planetary stability. Now, this has major potential risks in terms of the capacity of the planet to buffer the stress that we're posing. So this is one of the deep scientific concerns that are increasingly now
on the table when we analyze the risks we're facing. The fundamental one is shown on the screen here. I could pick many areas of research, but this is, I would argue, let's say, the higher order aggregate factor, which is of most important, which is the global energy balance. Everything that happens on planet Earth, both in the living system and in the non-living system, is all about energy transfer between matter and flows from temperature rise, freshwater flows, photosynthesis, all life on Earth. And what you see here to the left is the latest assessment of the energy imbalance on planet Earth. Because what happens is that solar radiation bounces and absorbs and creates and absorbs heat on planet Earth, returns as long-wave radiation, but it's stuck because of the greenhouse gases that we are emitting, and this causes the energy imbalance, where we today have the numbering of this, that 90%, which is a remarkable number, of the heat caused by our fossil fuel burning is not in the atmosphere, it's in the ocean. 4% of the heat from fossil fuel burning is consumed when melting ice. So this is another one of these paradoxical resilience factors in the Earth system, that while the Greenland ice sheet, the West Antarctic ice sheet, glaciers across the European continent, you've read of the disaster of the sudden huge flow of permafrost thawing in Barrel in Switzerland just a few days back. Well, that is consuming energy, which is buffering the Earth system, and it's only 2% of the energy imbalance that is in the atmosphere, causing the climate crisis, which has led us to the point where we are today, where we can clearly state as a climate crisis that we've reached 1.3 degrees Celsius of global mean surface temperature rise, and even touched a point above 1.5 degrees Celsius last year. That is a planet under tremendous stress, which is buffering and applying its biogeophysical processes, a resilience attempt to stay in a stable state. And you see the data of the ocean uptake to the right here. It's heat uptake all the way down to 2,000 meters of depth. An enormous thermostat physical contribution toward the stability in the Earth system. The second data is here. This is the annual update of the global carbon budget. Carbon, as you know, is the dominant greenhouse gas. 70% of greenhouse gases from our fossil fuel burning is carbon dioxide. What you see here is the timeline from 1850 until today, billion tons of carbon on the y-axis. The gray curve here is the hockey stick we just talked about. That is the carbon release from fossil fuel burning. In orange is deforestation. Is it all of this that has been aggregating in the atmosphere, absorbing heat? The answer is no. The dark green take-up under the zero line here is the 25% uptake of carbon dioxide in the ocean. The light green part is the 25% uptake from intact nature on land. And it's only this blue part, which is the residual remaining in the atmosphere, causing the climate crisis that we are today experiencing, all the fires, droughts, heat waves, massive expansion of disease patterns, human-reinforced storms. And if you look carefully at this graph, since we started the Industrial Revolution, the planet has been this remarkable friend. The more we abuse and release greenhouse gases, the more the planet has been buffering. And this is exactly the conclusion. A healthy planet with functioning biosphere is able to buffer and dampen the stress caused by our anthropogenic pressures. The problem is that unfortunately here, over the last recent decade, we start seeing cracks in this system. If you look at the data in countries like Finland, Sweden, Norway, but even in Germany, in Canada, forest systems are starting to show signs of tipping over from carbon sinks to carbon sources. We see major new science from the Brazilian part of the Amazon rainforest also having tipped over from sink to source. This is first signs of a planet being under stress and potentially starting to lose this resilience capacity. And we have the data on the risks here because we are seeing so strong signs of us undermining the diversity of life on Earth through biodiversity loss, both in marine systems and on land, which in turn makes the system, the whole Earth system, weaker to be able to handle this stress. So this is factor number 2. We're in the Anthropocene and the planet is under stress. The reason why we have such concern about this is that we have so much data showing that what we are threatening, namely the Holocene, is a remarkably stable interglacial state of the Earth system, which is so stable that I even choose to call it the Garden of Eden. The desired state of the planet that we all depend on, the state of the planet that is the basis upon which we have developed our whole modern civilization. And here's the data behind this. 400,000 years. This is ice core data in a superb recent summary of the evidence. We start over here. We are, since 1850 until today, you have the hockey stick of change. We've reached 1.3 degrees Celsius of warming so far, actually. We're heading towards 3.1 degrees Celsius. We'll soon see the latest updates. Just to kind of cut short a long discussion we could have scientifically, 3 degrees Celsius is a future where there's no evidence that we can support in a responsible way dignified life for 8, soon 9 billion co-citizens on planet Earth. That is simply beyond adaptation for billions of people and is therefore a path towards an unacceptable future. But we are already today outside of what I call the corridor of life. This is the last 10,000 years, the interglacial stable Holocene period, a warm interglacial. And can you imagine, the latest data shows, despite the variations, that this is a planet of 14 degrees Celsius of global mean surface temperature, plus minus 0.5. 0.5 degrees Celsius, and we are in the maximum range of variability during the entire Holocene. And here we have the latest ice age. And here you have 2 more ice ages, and we have been modern humans on planet Earth, the latest science shows, from roughly this point. So we've lived through 2 ice ages and 2 interglacials, and when we exit the last ice age right here, we are a few million people on planet Earth, we're hunters and gatherers, we live in caves, we have, to put it simple, a rough time. Until we come out of this ice age and we enter this extraordinarily stable life corridor. We barely enter it, and we go through the most important revolution of them all, the Neolithic. We shift from being hunters and gatherers to domesticating animals and plants. We become farmers. We settle down, and off we go in the community-based, sedentary diversification of talents that takes us to the point of meeting in Villars in June of 2025. It's a very comprehensive summary, I agree, of the civilizational journey, but it's basically what the Earth system science shows is the evidence. We depend on the stability of the Holocene. It's quite simple. What happens in the Holocene is that seasons settle down. Spring, summer, autumn, winter comes back repeatedly every year. Rainy seasons with roughly 25 rainfall events in the tropical zone repeats itself every year. It becomes worth the investment to plant seed, and you get the time to harvest, and it seems to repeat itself predictably year by year, which enables us to start the journey. What this scientifically means is that we draw 2 very simple but quite determinant or fundamental conclusions. Number 1 is that the Holocene is the only state of the planet we know for certain can support the world as we know it. The second conclusion is that this is the perfect reference point because we know so much about the Holocene. There's even a scientific journal called The Holocene. We can measure against the Holocene. We use the Holocene as our reference point for setting the safe operating space on planet Earth. And that is fantastic that we've come to that point. Now, the third part of this scientific journey is that if we start losing resilience, we also understand that the planet is a self-regulating biogeophysical system with interactions and feedbacks, and we have biophysical systems like the Greenland ice sheet, like the AMOC, the Atlantic Meridional Overturning Circulation of heat in the North Atlantic, like the Amazon rainforest, which are what we call tipping elements. Why? Because they have multiple stable states. Push them too far and they cross the threshold, and they will irreversibly shift their feedbacks from one state, a stable rainforest, to another state, a bush savanna. And we understand this quite well, and this is a risk we pose when we lose resilience. When we push too much stress to the system, the stability of the system is reduced, and the system can become more brittle and therefore fall over a threshold. Here we have the 16 tipping element system that we've now mapped. They are across the entire planet. 6 of them are up in the Arctic zone. They're connected via the North Atlantic through the overturning of heat in the AMOC, the Gulf Stream system, connected also to the Amazon rainforest, 3 systems down in Antarctica. You also have the tropical coral reef systems as one of them. I show this just to make a little reminder that we sit here in this beautiful village of Villars, but we depend on all these that are distributed across the entire planet. I call these today global commons. These are systems that we collectively depend on, irrespective of where we live, irrespective of what we do. The stability of these systems have repercussions on life support on the entire planet. Now, if you summarize these, they come with different risks. So here is the list of the 16 I showed in the rotating planet. It's the first time, it's a paper from 2022 that we published, led by David Armstrong McKay, where we for the first time were able to do a risk assessment of the temperature levels where they are likely to cross their thresholds. So what you see here in red is what we call burning embers risk confidence levels. The further to the right, the higher the likelihood of crossing a threshold. You see temperature on the x-axis. The circles here are the median numbers, meaning the likely levels of crossing a tipping point. And look at the first 5 that fall right between 1 and 2 degrees Celsius, which means that they're likely, according to the science today, despite the uncertainty range which you see, admittedly there's still uncertainty ranges here, but they're likely to cross the thresholds already at 1.5 degrees Celsius. And just look at those 5. The Greenland ice sheet, the West Antarctic ice sheet, abrupt thawing of permafrost, one of these rapid self-amplifiers if they lose carbon and methane, collapse of all tropical coral reef systems. I mean, this is livelihoods for over 200 million people. And finally, a collapse of the Barents Sea ice and actually also the Labrador Sea current. Those 2 ice sheets hold 10 meters sea level rise. Not that you would have a tsunami Monday morning, the day after you cross the tipping point. It might take 1,000 years to melt, but it would be unstoppable. Now, we use this science to set those lines in the sand, the boundaries, meaning that 1.5 degrees Celsius becomes a hard boundary, not a target, not a goal, as it often is portrayed in policy, but a limit, a boundary beyond which we take risks. Now, I just wanted to say very briefly that, for example, look at the Amazon rainforest here, which has a temperature median of roughly 3.5 degrees Celsius and a very wide uncertainty range. So that is what climate science says. The Amazon basin could withhold itself up until more than 3 degrees Celsius warming, which of course is, as I told you earlier, a very, very high degree of warming. Actually, it's even an unlikely warming for us ever to reach. Really, really, even if we follow business as usual, we're unlikely to do so. But ecologists, hydrologists, and other scientists tell us we're wrong on the assessment that the Amazon rainforest could cope all the way up to 3 degrees Celsius. Why? Because if we continue cutting down trees and losing biodiversity and changing hydrology, the system becomes less resilient and risks crossing thresholds at a lower temperature. So this is a proof point why we need something like a planetary boundary framework where we understand all the systems on planet Earth that regulates the stability on the planet. Finally, we also have to recognize the fact that we are now heading towards overshoot. We are all set to hold 1.5 degrees Celsius. Scientifically, this is very, very well established, so that's what I showed you just earlier. But we have come to a point where we are now very likely going to, already within 5 to 10 years, breach the 1.5 degrees Celsius limit and have a period, at best, of 30, 40 years of overshoot before potentially coming back below 1.5 by the end of the century. What you see here are the IPCC, the Intergovernmental Panel on Climate Change, scenarios that can still hold 1.5 after overshoot. Why do I show these? Well, because I conclude today, and I say I because we haven't really published this, but from the Potsdam Institute, our conclusion is that we can no longer hold 1.5 without ever exceeding it before coming back. That this is, to put it simple, the best we can offer today, meaning that we are unavoidably heading towards overshoot, but we can still potentially come back by the end of this century below that 1.5 degrees Celsius level. Now, what does this mean? Well, it means 2 things. One is that it will get worse before it potentially gets better. And every 1/10 of a degree means more extreme events, more droughts, more floods, more heat waves. But a big question is, why would we come back? And the conclusion there is quite straightforward. We can come back if we phase out fossil fuels, net zero by 2050, start removing carbon through carbon dioxide removal technologies, and invest in nature, invest in the resilience of the living biosphere. That is why, I mean, fundamentally and even urgently, we need a planetary boundary framework. And here you have the planetary boundaries, the 9 Earth system processes that we have now for over 15 years been studying, and where we have proof that they contribute to regulate the functioning, the resilience, and the stability of the Earth system. It's not only climate, it's also the biosphere boundaries of biodiversity, land system configuration, the bloodstream of the whole Earth system, the hydrological cycle, and the biogeochemical flows, particularly of nitrogen and phosphorus. But it's also the stability of the ocean, ocean acidification, air pollutants, which we call aerosol loading, the stratospheric ozone layer, and the loading of chemicals, novel entities like organic pollutants, microplastics, PFAS, nuclear waste, and all forms of cumulative chemicals. We have been able now, this is the 2024 update, we've been able to quantify all the 9 boundaries, giving us a safe operating space, which gives us a high likelihood of remaining in a stable, for us humans, desirable state for the planet. But this is the latest assessment. We are in a situation where 6 of the 9 boundaries have been breached. And that's what you see here. And the range between the green zone and this circle here is the uncertainty range in science. That's what I call the danger zone. You exit the safe zone, and things can happen, but we're not entirely certain. Enter the red zone, and we enter a terrain of high risk, where we have more and more evidence of really being at high risk of causing irreversible changes. This graph kind of proves the point that we are not to be surprised that we're starting to see accelerates of warming and also risks of losing some of the resilience in the Earth system. It also shows that we have to come very rapidly back, and it's not only about carbon dioxide. So this means, what is the future then? Well, it is about us transforming back into a safe operating space, but the unique feature of the planetary boundaries is that it means operating within global budgets. Now, we've never done that before, to have an economy, to have societies, to have companies and countries that operates within finite resource budgets. Now, we have, though, been starting to learn how to do it for one of the boundaries, namely climate. As you know, we have, once you've defined a temperature limit, 1.5 degrees Celsius, that translates to a carbon budget. A carbon budget translates then to a trajectory, a pathway for a future, an orderly phase out of those fossil fuels. Here you have the latest, no, not even latest, the second latest update of the remaining global carbon budget. So we have consumed the blue part here, which was the original budget we had, according to science, to be able to hold 1.5 degrees Celsius. What remains is 200 billion tons of carbon dioxide. Now, actually, I said the second latest because unpublished data shows that the budget is now down to 150 billion tons of carbon dioxide. The reason for this is that we continue increasing emissions, unfortunately. But 200 is equivalent to only 5 years of emissions. So this is, as you can imagine, why we have this transformative urgency point. But this is something which is really important to recognize, that the future is about accounting within budgets, because the same goes for nitrogen, for phosphorus, for land, for fresh water, for biodiversity, that we have to stay within global budgets. And this one on carbon is the one where we've come furthest in terms of defining that budget. And the journey we have just to have a safe landing on climate is what you see on this graph. This is still unpublished data, so bear with me here, but this is the latest update on, from now up until the end of this century, the journey on fossil fuel phase out in gray, reaching a net zero world economy by 2050. You see this dark gray part is the emissions from the food system, agricultural emissions. This is the carbon part of food emissions that need to go from source to sink. That's what you see in orange here, over the next 30 years. That's a green revolution that is factored into the climate models. And then you have the carbon dioxide removal technology scaling here in yellow, which is a massive and very optimistic assumption that we will be able to scale CCS, carbon capture and storage, different forms of direct air capture, to over 5 billion tons of carbon dioxide per year. And then there's a very optimistic assumption that we will be able to keep intact nature on land and the oceans intact and able to continue absorbing roughly 50% of the carbon dioxide. That's our journey. That's the journey we need to follow to be able to come back, to have any chance of coming back after overshoot. What does this tell us? It tells us that we need to operate not only within budget, we have to operate within planetary boundaries. The climate challenge is not only an energy transition. The climate challenge is a global sustainability transformation. And that is what this tells us. Can we do it? Well, the answer is that we have actually the solutions for most of the transitions we require to do. But it's no longer a linear journey. It's about pushing ourselves out of the inertia of the fossil fuel-based, linear, resource-inefficient value chains we have in the economy today, by pulling down the limits to this, or the lock-ins we have in vested interest, in erroneous policies, in unleashing innovations, in giving the right incentives, for example, through a price on carbon that would make fossil fuel-based energy systems more expensive compared to green technologies, to be able to start a journey where we start surfing downhill fast in the same way as we've been surfing uphill through the hockey sticks in the wrong direction. Can this be done? Well, already in 1962, Roger Everett postulated the theory of diffusion of innovations, showing that if you get innovators, early adopters reaching roughly 20%, you can actually tip over the inertia in a whole population and kick off S-curves of exponential growth if you have the better idea, if you have a better solution. Now, we know from ample evidence that we're sitting on a better idea, that the fossil fuel-driven, linear, planet-damaging processes driving our current economy is a dead end, but a transition into a resource-efficient, circular, zero-carbon or green energy-driven world economy gives us multiple benefits, not only in terms of efficiencies, competitiveness, even more jobs in most economies today, but also in terms of health, in terms of security, and in terms of stability. So given that we have the better idea, we could actually tip over the inertia in the majority by having a large enough minorities. The question is, are we starting to reach double-digit number on minorities of the better solutions? The answer is yes. And we're doing that very much through thinking that is driven by, for example, the work, well, it actually starts here. I mean, you could take one step back here. Operating the global economy within budgets, is that a new idea, you may ask? Well, the answer is no. Herman Daly, already in the 1990s, postulated the idea of a steady-state economy, which is an economy that operates within the finite boundaries of the planet. Partha Dasgupta quite recently put out a whole study for the UK government on a world economy that operates within finite boundaries. So this is not new. It can be done. We also have successes happening in the past, and I just want that to be also in this room, that is it possible really to operate major changes for the whole planet based on science and policy change? And of course, you have one story, one of the 9 boundaries, where we actually succeeded in a remarkably efficient way. And that was the threat, the existential threat of depleting the stratospheric ozone layer in the 1970s, 1980s. It gave the Nobel Prize to Paul Crutzen, Mario Molina, and Sherwood Rowland in 1995. They worked hard on proving that we were, through the emissions of chlorofluorocarbons, chemicals that we use in air conditioners and refrigerators and spray bottles, were destroying the protective ozone layer. It was actually assessed that we would be at risk by 2065 to have a complete ozone hole across the southern hemisphere, which would actually be an existential threat to humanity. And what did we do? Well, we trusted science. We had massive work up until the mid-1980s, signing the Montreal Protocol in 1987. This was science informing policy with a regulatory scheme for global action. And we then phased out the chlorofluorocarbons. And today, we're actually repairing. We're seeing the ozone hole being repaired. So we actually have done it before. We have been planetary stewards once before for one of the planetary boundaries. And now then back to this double-digit question. Well, this is just energy, renewable energy adoption. Here you have in the global south, the levels reaching 10%, the global north adoption of green technologies for energy reaching double-digit numbers of 20%. It's rarely talked about that Latin America, South Asia is actually moving very fast on exponential S-curves of adoption of renewable energy systems. When it comes to transport, the classic story is the one you see to the right there, Norway, with electric cars today following a very clear S-curve. 90% of sold cars in Norway are fully electric today, without subsidies. This is something, there were subsidies in the beginning, but today it's simply a self-reinforcing, positive trajectory because it's simply the better idea. But what you see on the left-hand graph here is Denmark, which has now reached 60% of EV penetration in the economy. Also policy and innovations and preferences among Danish citizens moving really fast in this direction. I've also played, to close, myself with something that I'm always accused with, to say, well, sure, you can do a lot of things on electric mobility that is moving on its own, but it's much more difficult with difficult-to-abate sectors like aviation, steel, cement, fertilizer, the food system, of course, plastics, chemicals, mobility transport, for heavy trucks not least. But when you scan through what's happening in business in particular, there are basically solutions across all of these. Admittedly, they have not reached the stage of commercial scaling, but for many of them, at least my assessment would be that they have a green light of being basically scalable, competitive, and able to deliver at large scale, as long as we just do some corrections of the policy failures we have across the world. Some of them are still admittedly in the red zone of still being piloted and challenging, but it's quite interesting that we can no longer say that we cannot solve the climate crisis because we don't have scalable solutions. Actually, I would argue that we reached a Montreal moment for climate. The science is settled, policy agreements are in place, the Paris Agreement is signed, we all have the numbers in place, and we also have the solutions, just as during the Montreal Protocol. So this means, to leave you as a final conclusion, this lecture tells us clearly that we're outside of the safe operating space. We are in danger. The planet is in a danger point. But my conclusion, at least, is, and I say my because science is also normal distribution here, that we are not in the red zone yet for the planet. The planet still, despite all the stress, is still dominated by dampening feedbacks. It's still remarkably biogeophysically resilient. And this is something that we should humbly recognize, which means that when Billie Eilish recently was in Berlin singing about the fact that the party is over, which I totally agree with, the unsustainable fossil fuel-driven party is over. But scientifically, I would argue that the game is not over. We still have a chance. The window is still open, even though it's rapidly closing, for a transformation, for a safe landing within a stable, manageable, and resilient Earth system that can support our and future generations. Thanks for your patience.